In this video, we present a brief illustrative example of a microgrid during the islanded operation. The main learning objectives will fall under two questions. Firstly, how will the adaptive protection work during the islanded mode? Secondly, how will the adaptive protection help avoid the selectivity issues in microgrids? The implementation of the protection schemes in microgrids is typically more complicated than a normal radial distribution feeder. This is mainly due to the fact that many factors which have serious impacts on the performance of the protection scheme are more frequently changing in the context of a microgrid. For instance, the configuration of the microgrids largely changes not only during the normal operating conditions, but also during the transfers of their operating modes, meaning grid-connected or islanded modes. Moreover, the point of the connection type and power production of the electrical components largely vary during the operating of microgrids over time. These frequent changes in the mentioned factors may require to continually adapt the protection according to the new operating states of the microgrid. Therefore, the adaptive protection is implemented to ensure the accurate performance of the protection during all the operating conditions of microgrids. In this video, we analyze the case that one microgrid becomes islanded from the external grid, while its protection settings remain unchanged according to the ones of the grid-connected mode. Let's now consider the microgrid shown in the slide. In this example, we create an islanded microgrid where switchboard 1 and switchboard 4 are assumed to be disconnected from the microgrid. As shown, switchboards 1 and 2 and 4 will form an islanded microgrid together. In this islanded microgrid, we assume that the generators in switchboard 1 and switchboard 2 do negligibly participate in the fault current due to their indirect connection through the power electronic converters. However, the generator in switchboard 4 is assumed to be a directly connected electrical machine. Therefore, it provides a certain amount of the current during the fault. This fault current will pass from switchboard 4 to switchboard 2. However, in general, the fault current by the generator is much lower than the fault current which is provided by the grid. In this slide, we show an example of the time current tripping curve of the relays. As it is shown, we assume that circuit breaker 2.2 and circuit breaker 4.2 would react at 0.1 second for the large amount of the fault currents. Circuit breakers 1.2 and circuit breaker 2.1 will also disconnect within 20 milliseconds after the fault. We assume that in this example, the fault current is 2 per unit, which is below 3 per unit for the short circuit current with a short delay trip. Since the amount of the fault current by the generator is low, then the relay may trip with a large delay. In this slide, the delay trip is shown where the tripping time is at the intersect of the overload region and the 2 per unit fault current. For instance, in this case, the relay may trip after 40 seconds. This large delay in the operation of the relay will likely make the generators unstable. Let's recall from the other video where we discussed the instability of the generators during the faults. If the fault clearing time is greater than the critical clearing time, then the generator becomes unstable. In other words, if area 1 becomes larger than area 2, then the generator is not able to return to the nominal rotating speed. These delays associated with the protection may also lead to a serious damage to the electrical equipment. To avoid the instability of the generator in this example, the current time tripping curves of the relays shall be adjusted. For this case, the base trip curve shall be shifted from the left, where we have to dynamically modify the tripping curve. For this example, we shift the current of the base curve from 3 to 1 per unit. In this slide, the intersect of the newly shifted trip curve with the fault current of 2 per unit is shown. The relay will trip, in this case, around 20 milliseconds, which is remarkably much lower than 40 seconds in the previous case. This way, the adaptive protection helps ensure the proper operation of the protection scheme when subfactors of the microgrids, like their configuration, would change over time. In this video, we briefly discussed the adaptive protection for an islanded microgrid example. As the level of the fault current is relatively low in the islanded microgrid compared to the grid-connected one, we have to adjust the current time tripping curve of the relay in such a way that it trips much faster for a lower amount of the fault current.